Okay, all right. Good afternoon, everyone. So before we start the lecture, just a couple of things I want to mention. So I think we only have like a couple of lectures left. So today we'll talk about multimodal learning, foundation models. Thursday we'll talk about Gen AI for medical imaging analysis, specifically GANs. And then the next week will be spring break, so we don't have classes. And we'll have remaining 4 lectures. One is for Gen AI, and also adversarial robustness for the model, and also we'll talk about federated learning for medical image analysis. Then the rest of the 4 lectures will be focused on final project presentation. Okay, so I will send out a sign-up sheet. Basically, your team, or if you're doing a team project, you will present either of these 4 lectures. Okay, if you're doing individual project, then you'll be the only presenter for that. So we're using the same this sign-up sheet. One thing I noticed is that I think we have 28 students, but here I only see like 20 students here. There must be some student didn't put the name, or maybe their team names here. So if you haven't done so, please do this. So I want to know how many teams are there, right? So I think it shouldn't be over like 24 teams. So my plan is each of the lectures will have like 5 or 6 team presentations, right? Each will take like 10 minutes, and to go over the progress, the problem, and some of the latest result. And I may ask some questions or give some feedback. Okay. So one thing to note is that don't be afraid to present early, right? Like April 8th. Like you may not complete like your project. That's totally fine. So like my evaluation for this presentation will be not based on like if you have complete the project or not, right? So I just basically want to see how you present it, right? The overall story and what do you have so far. So even if you complete like only 40 or 50% of the project, that's still fine, right? Okay. So I know some student may want to sign up in a later class, but if that's the case, if we don't have many students presenting the first 1 or 2 classes, I may move randomly, right? Randomly pick a couple of teams to move that in front. Okay. Okay, so I will send out this announcement, right? So you guys can, select the time you guys want to present. But it's gonna be all, starting from April 8th. These 4 lectures will dedicated to presentation. So if you are enrolled in the in-person session, please come to the class and do the presentation in person. If you are enrolled in the online, synchronized session, you should present during the same lecture time, but via Zoom. If you are enrolled in the asynchronized, session, ideally I would encourage you to, present live via Zoom. But I understand some students choosing the asynchronized because they have different time schedule. They may working during the daytime. The worst case is, the team has to record the video recording and send it to me, okay? And later I will post on the course material, right? Because every lecture will be made available to everyone. So if you are not able to do this at least online synchronized, then you have to record the video and send it to me, okay? But the synchronized live, should be present via Zoom, and of course in person you have to come to class to do the presentation, okay? Okay, so that's something I want to quickly mention, and let's go back to the lecture. See. Okay. Other thing is I've extended the programming assignment too by a couple of days. So you haven't finished, try to wrap up everything, because I won't extend longer, because you have to work on the assignment 3 and also the project. The TA will grading the programming assignment, so I asked him to definitely complete the first assignment grading during the spring break, so you will receive feedback. Okay, question?
For this assignment, do we have any an ideal score that will be for which we will be judged against? So like when we're evaluating and presenting this DICE scores and the overall results for different boards, is there any ideal score that we should achieve in the metrics?
No, there's no ideal score. I mean, ideal score will be 100%, right? So if you predict everything correctly. But so I think as high as possible you can do. But if there's the DICE score or accuracy is less than 50%, there must be something wrong with the model, right? Because if it's just binary, right? If you only have 50%, then that's kind of a random guess, right? So there must be something wrong with your model. So ideally, I would encourage you to try, achieve as higher accuracy as possible. But I don't think you can achieve 100%. Yeah, so there's no perfect solution, but just try your best to get the higher accuracy as possible. Okay. Of course, make sure you have everything I ask for, right? Writing the technical report, right? Ask to report the accuracy or confusion matrix or show some examples. You have to be showing all those things, right? If you're missing some of the parts, then you will lose some points. Okay. Okay, all right. So for today's lecture, we'll talk about foundation AI model. So you probably heard a lot of these buzzwords, right? Foundation models in the recent years, right? Because we do have a lot of data, and we are able to using this transformer architecture, trying to unify different modalities and train a very large model, and it's going to be supposedly to perform very well, right? So the idea or the concept of the foundation model is that we want to train a model on a broad scope of the data, right? So not necessarily a single modality, but if you can have multimodal data, right? Text, speech, audio, video, everything you can collect, then we want to, and they share some common or mutual information or complementary information, we want to leverage that, right? So we want to learn a very good knowledge representation so that it can perform very well on a wide range of downstream tasks, right? So in this case, we call these models a foundation model, right? So just to mention a couple of them, right? So I'm sure you guys have been try out or using GPT, right? ChatGPT, right? So it's type of foundation model, right? So it's able to generate text and able to understand a lot of small nuances, right? You can do this kind of dialogue and help you answer all kinds of questions, right? So it's trained on a large corpus of internet data, right? Well, you may ask, right? Why do we care about foundation models, right? Before even heard of this kind of idea or the concept of foundation models, we seem to be fine, right? So we can develop a specific model, right? If we make the analogy of foundation model as generalist, right? So before we may have a lot of specialists, right? So we can customize a particular model to perform a specific task, right? Classification, we can train many specific classification tasks, right? Maybe each model for each specific data set, and we can train many object detectors, right? And also semantic segmentation models. But why do we care about a foundation model? So there's actually a couple of benefits, right? So it's provide a very powerful starting point, right? Because we are learn from a lot of data, right? We can learn this from the unsupervised or self-supervised learning, right? Which we talk about in the last 2 lectures, right? So we have a lot of self-supervised learning technique, and we can leverage a huge amount of unlabeled data, right? So this will help us to learn a very good representation. And a lot of time, a very good starting point is going to be, ease a lot of tasks, right? So you don't have to do a lot of, computation or fine-tuning process, right? If you don't have a lot of resource. And if you have a very good, pre-trained model, right? So then, when you fine-tune it for the downstream specific task, then you may not necessarily need a lot of data, and you can do a very quick adaptation. And also, because these foundation models, right, learn a very generalizable knowledge, and is easy to transfer to a different task. Okay, so we don't have to necessarily train a lot of specific, models. We may just leverage a single foundation model and do easy or quick adaptation. And the foundation models can, support the development a lot of advanced AI applications, right? Like this chat box, virtual assist, right? Image recognition and autonomous driving vehicles, right? So we are now talking about agentic, era, right? So we can build a lot of AI agent, right? So a lot of agents will leverage all these foundation models to perform multiple tasks. So this is like a like a concept, right? So how we can train this foundation model, and once it's trained, right, how we can adapt to different tasks, right? So here, a general foundation model, we can leverage all, basically different modalities you can think about, right, in our daily life, right? Definitely we have a lot of text, right, from, internet, Wikipedia, or books, or articles, blogs, right? And we also have a lot of images, right? A lot of social media and also speech. Structured data can be tables, right? So a lot of specialized cases, right, like financial or maybe healthcare, we do have a lot of tabular data, right? So those tabular data has specific meanings, has specific structures. And also sometimes we may have like 3D signals like RGB depths, right? So a lot of these like LiDAR or maybe other type of sensors can provide 3D information, right? So we can also leverage these 3D signals and to jointly, right, hopefully these different modalities are complementary with each other. We can train them together to form a very strong foundation model, okay? Then we can using that, foundation model and do some adaptation. And we also talk about, right, efficient fine-tuning, right? We don't necessarily have to, train the entire model, right? Because usually these foundation models are very large, right? Using maybe transformer, many layers of like, self-attention blocks. So it usually has billions of parameters. Train from them or fine-tune them altogether is not feasible. So we can do some efficient fine-tuning, right? You can using LoRa or using adapter or maybe just fine-tune a specific layers. So we can do the quick adaptation and, is able to fit the data distribution of a downstream task. Okay, so I think throughout the lectures, different lectures, we've kind of mentioned a couple of like so-called foundation model, right? So in the last self-supervised learning, we also mentioned the CLIP model, which is using images and text, right? So we can do paired images, right? In the embedding space, we can make the paired image, their latent space should be aligned with each other. Non-paired images, right? The text and image, they belong to the different semantic concept. They should be far away from each other, right? From the embedding space. So just, maybe mention this again, right? So I know we've talked about, or see this images before. So this is how this clip was trained, right? Using the contrastful learning strategy. So you have these text data, right? So you can go through the text encoder. This could be a transformer architecture, right? So do the text embedding, and you get these, latent features for different text. Simultaneously, right, you are also feeding these images, right, to this image encoder. This could be the vision transformer to encode the image features, right? Have these feature embeddings, showing in the green color. And you can do this contrastful learning, right? So whatever, the data, right, the text and the images, they belong to the same class. You should make them close to each other. If they are not belong to the same class, you want them, the embedding space, the cosine similarity should be, less, right, a small value. And once you do this kind of self-supervised training, right, using this contrast learning strategy, then you can do this zero-shot learning. Okay, so that's one very good property of this CLIP, model, that you can do the zero-shot prediction. So this zero-shot prediction means during the test time, if you are given a totally new class or image belong to a totally new class, you've never seen this during the training, and you are able to retrieve the closest, right, text embedding, right, and trying to predict what that class is, right? Because here, these text encoder, basically you can, do this encoding from all this kind of vocabulary, right? So in this case, you basically retrieve whichever the text embedding that is close to the, input image. Even though this is like an unseen class, right? You are able to retrieve the corresponding text embedding and make that as your prediction for the class. Okay, so we can see that these CLIP model has been used, right? So do this kind of image classification, and so here I show a couple of specific examples, right? So this one is predicting this guacamole, right? So it has like 90% confidence, right? So this is so the prompt is a photo of something, right? The something is the model has to predict. Okay, so it's able to predict this is guacamole with 90% confidence. And this is another example, right? So a photo of something, right? So this is predicting a photo of a television studio. Okay, so yeah, you can see there's some cameras, right? A lot of lighting conditions, right? Just like a studio. And this is another domain, right? So maybe this has never been showed, right? This is like a remote sensing images, right? So I'm not sure if the CLIP, the pre-trained data contains such, remote sensing data. But in this case, right, this is kind of low resolution and from a different perspective, right? So usually the training data is like the third person, right? So like ground images, but this is like a satellite, right? Like a top-down view of the field, and this model is still able to predict, right? This is a crop land, okay? And when we, also feed into a different domain, which is the medical image, right? So this kind of microscopic image, right? So this is also predicting this is lymph node tissue, okay? So you can see this is a very strong, generalization capability, is able to predict very accurately in the zero-shot setting. And this is, we can also do, action recognition, right? So in this case, for a video, right, maybe we can randomly select a couple of frames, right? So the CLIP model cannot accept like video clips, right? But it can accept like frames, right? You can actually feed these video frames to this CLIP model and ask it to predict like frame by frame manner, right? So in this case, you may select a couple of video frames and feeding into this CLIP model is able to predict a photo of a country line dancing, okay? So this video is took from this Kinetics 700, which is a video action recognition database. Okay. So there's also a lot of applications, right? You can build applications by using CLIP as the model as the engine, right? So you can do semantic image search. So you can maybe just writing a couple of descriptions, right? Animals in the long grass, right? So if you type in these text prompts, then the model will return, right, whatever the images fits this description, okay? And here another application which is from our group. So we are also using the CLIP model for action recognition. So this action recognition is more specific. So we are doing this children with autism, right? So this autistic behavior recognition. So for the children with autism, they usually behave from these kind of so-called stemming behavior. So like some of the actions or activities are repetitive, right? So like head banging, spinning, right? So they usually do this multiple times, and depending on the severity of their symptom. So the idea of this project is you want to, using this kind of clip model to help improve the action recognition performance. So how we can, using the clip model to help this kind of healthcare application is basically what we do is we know the action label, right? So this is arm flapping, and this is hand banging, right? So this the data set will only give you this kind of very short description or action class, okay? Spinning, hand action, etc. So very short description about the action. So but what we did is we go to like Wikipedia or maybe some medical or journals related to the autism domain, and we trying to enrich the description, right? So or maybe you can just feeding this into like a GPT model, right? Ask it to maybe enrich the description, like what is the arm flapping in the autism behavior. So what we get is, like a very long description, right? So like arm flapping is one of the stemming behavior, blah, 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 right? So basically describe what this, movement look like, right? So we can do this for the other actions. So once we have these very detailed description of the actions, we can, using a clip model in this case, to help understand, to provide some of the semantic meaning based on the text, okay? So basically, we are feeding these texts, right? Spinning in something, into this clip text encoder, okay? And this text encoder will give you some of the text embedding, right? Describing the spinning action, okay? At the same time, we do have the input video, right? So we will feeding that into video swing transformer. So this is a pre-trained action recognition model using the swing transformer architecture. So we get a visual embedding as well, right? So we have the V embedding. So here we have this language, right? The text embedding. So in this case, we can do some contrastive learning, right? Because when we're doing the training, we know the video and also the corresponding action label, right? So this is spinning, and we can, make sure they're, embedding, the text embedding and the visual embedding should be close to each other, right? Because they are describing the same action, okay? And you may wondering, okay, why do you do this kind of enrich the description in the first place, right? You can essentially also feeding spinning the action class into the text encoder, right? So yes, we can do that, but a spinning, right, is very ambiguous, right? So you can do a general like spinning. Dancing can be a spinning, right? So here we are enriching, using some of the, or you can do the manually enriching, right? Maybe using Wikipedia definition or using GPT to help you enrich description. We can generate the description that is specific in the autism domain, right? So how they spin and the body movement related to the autistic children, okay? So in this case, we get a more accurate description. Then hopefully this will align well with the visual cues, okay? And one good thing about this is we can do this fairly easily, right? So this is kind of comes for free, right? So generally this text is very simple, right? So we only have like 7 or 8 classes, right? We can easily get the definition from Wikipedia or using GPT to generate these descriptions, right? And the clip model, we are just using the pre-trained model. We are not doing any of the tuning. So basically, we are using additional, or we consider this as an auxiliary branch, right? Trying to help or enforce the visual representation to learn better from the video, okay? So, and we show that, right? Without these text, branch, right? So it's visual swing, transformer. Only using the video, we are only able to achieve less than 90%, right? 88%. But if we are adding the language, the text, right? So we are able to improve by about 2%, right? So if we are using some pre-trained model, we are even to, as compared to this, pre-trained model, here is like a train from scratch. This is using a pre-trained model. if you do this comparison, we're able to achieve like almost 4%, right? So this is like a easily obtained gain by using these off-the-shelf language model, right? Using the clip text encoder. So that's another very specific example, right? So how you can using these, pre-trained foundation model, right, to leverage that knowledge in some of the downstream applications. And of course, we can also apply this to the medical domain, right? So we can develop this medical clip, right? So it's able to answer, questions specifically related to the medical domain, right? So maybe you can feed into a medical image, CTMI, etc. So this model is able to provide some, accurate description for that. And also can do this visual question answering, right? So again, just giving a question, and the model is able to, like the clip model is able to, extract the image features and able to, provide some answers that may be related to the question. Okay, so here are some of the specific examples they are doing using this. This is the chest X-ray, right? So this is maybe a CT image. B is a CT image, and C is the MRI, the brain scan, right? So you're able to provide these VQAs, visual question answerings, in different imaging modalities. Okay. Okay, so that's the clip example. Then we can using that for a lot of application, right? And in terms of in the medical domain, one fundamental task is segmentation, right? And also in the general vision domain, segmentation is also a really important task, because a lot of time we need to know the class of semantic label for each of the individual pixel in the image, right? So so there's a general foundation model for segmentation called segment anything, right? So it's short term as SAM. It's developed from Meta AI research. So this is like an overview of this SAM model, right? So it's like a promptable segmentation. Basically, it can take different type of like prompt input, right? So not necessarily like user have to give an image and it will generate a mask, but the supervision or some of the initial prompt can be like simply as a couple of points, right? So you can quickly provide some point, right? So the green can be the foreground, right? The red can be another type of class or background, and based on that, the model is able to generate segmentation mask. Or you can provide a simple bounding box, right, as the prompt, and is able to generate a very fine, detailed segmentation mask. Or you can, maybe provide a very simple mask, right? So a very quick annotation of the regions is able to refine that to give you a very accurate segmentation mask. Okay, so this is like the very high level idea of the model, right? So there's a prompt encoder, right? So maybe this is a point bounding box, or simply as a text, right? I want you to segment maybe the cars, or maybe some other objects in the vehicle. The image. So these prompt encoder will basically do some embedding, right, to generate those tokens. And of course, we'll have an image encoder, right? So which is doing the heavy lifting to encode the image into the latent representation. And then later we can do this kind of mask decoder, right? So the decoder will basically generate a mask. And another contribution for their paper is the data, right? So they basically build a large scale images with billions of 1+ billions of masks, right? So you can see they have a lot of images and annotations to train their model. And they also kind of proposed or streamline annotation process, right? Not all these 1 billion images or masks has been manually annotated. They actually come up with some automated process to facilitate or ease the annotation task, right? Because if you're doing this manually, you can imagine how many labors has to they have to pay, right? So like maybe a lot of annotators to do the annotation. So they're actually using some automated process, which we'll talk about later. Okay. So and later they also come up SAM2, which is their improved version, so right, to improve the efficiency and also improve the accuracy. So a lot of time you can using SAM on some of the resource limited devices like mobile phone to have a faster inference speed. Okay. So their model is open sourced. Okay, so I provide this GitHub link, right? It's on the Facebook research. This is SAM2 version, but they also have the initial SAM version. So you're welcome to check their GitHub repo, and if you're interested, you can download their models and play with their models for your own application. Okay. So as I mentioned, right, so the SAM is a foundation segmentation model. It's open sourced and developed by Meta. And they are building upon using the backbone of the vision transformer, right, because we are dealing with images and we want to leverage the state-of-the-art architecture to train this model, right? So this is just a very quick recap. You've seen this many times, right? So this vision transformer, the idea is just to divide images into patches, right? Do the self-attention mechanism in this transformer block. And they able to accommodate or accept different types of prompt, right? So it can be point, bounding box, mask, or simply text, right? So this is like a most convenient format, right? A user just typing some simple text, right? So I want to segment, right, a cat with black ears. So the model will able to predict or segment out this specific cat, which fits this user provide the prompt. Okay. And this is their architecture, right? So we've described this. You have this prompt encoder and image encoder. Then you have a lightweight mask decoder to generate the mask. And there's not much, nothing fancy, right? So basically, this image encoder is like a vision transformer. And then here you may have some of the for different prompt type, right? So you may involve small designs, right? Like for this mask, they may using some conv layers, right? So mask is like an image, right? So you can using some conv layers to extract some features, and then you will combine this with this mask decoder, right, to generate the predict mask or segmentation map. And here is like a close look, right? So how their architecture look like, right? So these are their specific dimensions to encode the images, and they have, right, these self-attention, right, the vision transformer, and a couple of MLP layers. So these are more like a very standard stuff, in the architecture. And eventually you can compute the IMU score, right? So basically that's the metric used for segmentation task. And one significant contribution is the data set. They curated, right? So they create like the largest ever data set, right? So it's like 11 times more images than any previous data set, right? And has significantly higher resolution, right? So usually maybe a lot of images like ImageNet, maybe you have very low resolution, like 200 by 56 by 256, but they were able to collect even higher resolution images, right? Because a lot of time we are dealing with varying resolution images. Some of them are very high resolution. If your model is trained on like a single, very low resolution, it may not able to perform well on some of the higher resolution images. So they trying to kind of also collecting a lot of higher resolution images, right, to increase the diversity of the data set. And of course, right, so with this large scale data set, for the training, they also need a lot of annotations, right, than the mask. So they have like 400 times more mask than any previous data set, like for segmentation, and also have very high quality mask, right? So you don't want to provide some very noisy supervision, right? If the supervision is noisy, then the model may not be able to learn well because some of the classes may confuse the model. So their data set, it's called this SA1 billion, right? So we have 11 million images, 1.1 billion segmentation mask, and 99% of them are generated fully automatic, okay? And they also have higher quality mask than professional annotators in 500 image samples. And so they were released by researchers from Meta. And this shows you, right, so how they collect this data set. So they are basically collecting images that cover different locations, right? So we don't want the model to be biased, right? So only collecting images that describe a specific region, right? Maybe in the North America region, then there could be a lot of bias, right? Like a lot of culture, environment things may not be covered, right? If you like Africa, Europe, Asia, they have a lot of their own cultures, right? So they want to be more diverse on that. So they are collecting, this is like kind of statistic, right? So have Africa, countries and the images and the mask they've been collected. And they are also doing this kind of comparison, with other existing database, like the COCO is also a very important or famous database for object detection and also segmentation. Okay, and once you collect these data, right, so they want to, do this kind of annotation. So basically, just a long story short is they have different stages to build this kind of annotation. Of course, the lazy way, or maybe the most time-consuming way, is just ask, maybe, if the company have a lot of money, they can recruit a lot of annotators, right? Or maybe distribute the task to some of the companies to do annotation. You can have a lot of annotators, train them to do the annotation. But what they do is you can first build maybe label a small amount of data, right? Of course, you should also leverage whatever the data is out there, right? So a lot of existing database like COCO or maybe other segmentation models with highly accurate label information, you can using that as your initial data to train the SAM model, right? So you don't have like a code to start, right? So you can leverage these existing model database to train the SAM model, and also label a small amount of your own data and to fine tune it so the model is able to perform well. Then you can using that model to generate the mask, right? Rather using the annotator to do everything from scratch, you can using this AI model to generate some initial annotations, and maybe we can just quickly check if there's anything mislabeled, right? So they can really speed up the process, okay? So, and you can train this in an iterative process, right? When you collect enough high quality data from your own database, you can basically retrain the model again, so the model can be, the accuracy can be improved, right? In the next batch of data, then maybe there's even less misclassification, right? So you can get more high quality data more easily, and you can again feed that data, going back to the training data pool and retrain the database. Okay, so that's some of the they have a different stages, right? Like a semi-automated stage and also the fully automated stage, trying to label all these data, then they can train this model to have a very strong foundation model for segmentation. Okay. So let's look at a couple of examples, right? So here they do some evaluation. They can do the zero shot with prompt, right? So you can basically collect a couple of points, right, on this object for this dog image, right? So these are the points you can collect as the prompt. Then the model is able to, based on that, and segment these foreground, which is the dog image, right? So which is very accurate if you look at the contour. And this is a detailed, result, showing the using the IOU as the performance, right? IOU delta at the one center point, right? So delta means the difference, right? So how many these kind of data set, they are able to perform a much better gain, or maybe for some of the data set, they kind of degrade a little bit. But on the majority, right, so that in the zero shot, all these data set, they have a significant gain, right? Some of them can be like 40% improvement. And this is another example, right, to do the edge detection, right? So edge detection is also basically you can extract it from like a segmentation mask, right? So not distinguish different classes, but you are able to segment those kind of salient object from the background, right? So you can have these edges. And this is also, they can do the zero shot, object proposal, right? So they are using, test out on these LVISI data set. And these are some of the results they have. And they are divided by, different categories, right? Small, medium, large. Some of them are frequent, occurred object, right? Some are really rare. So I think they are perform really well on some of the rare objects. And this is another example on the instance segmentation. Okay, so again, using the COCO and the LVIS data set. So they have the average precision and also, specific, right? Small, medium, large, just like a subcategory of the evaluation. Here are some of the visual results, right? So using the SAM, right? So doing the segmentation. So I think this one, some of the examples are really good, right? So the result. Okay. This is another example. I'll go to the next one. So basically, you've seen all these examples, right? So this is really the SAM provide a strong performance, right? And you can readily apply this, or maybe directly do the zero-shot segmentation, right? If your domain basically doing general image domain, maybe you don't have to fine-tune the model, right, on your own data set. Because, if your data set bears very similar distribution, their training data, then you basically can just, use directly using their trained model. But for different domains, right, like medical images, right, so we do have significant differences, right? Maybe their training data hasn't been exposed to some of the imaging modalities, right? So how can we adapt SAM for medical image analysis, right? So I wanted you to think about this, right? So how can we adapt the SAM model for medical image analysis?
Like during the homework, find cancerous tissue quickly.
Yeah, so like if I have a new database, right? So how we can adapt the SAM model? Let's say I give you ultrasound imaging, right? So maybe SAM hasn't been trained on ultrasound before, right? So how we can adapt the SAM model for ultrasound image segmentation, those things.
By using contrastive learning some approaches?
By using contrastive learning to do what?
I mean, giving some images of the ultrasmall and try to see if the model's output kind of like matching with that. So that type of law, like fine tuning on the
okay.
Something like this.
Yeah. Yeah. So you were saying we can using some medical data and just doing some continual fine tuning, right? So using contrastive learning within the self-supervised manner. Yeah.
Mm-hmm.
Yeah. Okay. Any other?
I have a question here. Because SAM was trained like as a foundation model, like in theory, it should have, because that foundation model should be directly applied to medical image, because I believe like segmentation is pretty low-level task where we have these shapes. Ideally, should work like RSC, like REs, but maybe it doesn't work because there's something different.
Yeah. Yeah, some of the images you can directly apply. I think they show some, or actually there are some studies when they released the SAM model and the paper. There's a lot of people trying to adapt or maybe just to evaluate SAM on the medical domain. So directly apply SAM to like a cell segmentation or chest X-ray, CT segmentation, and trying to identify, which image modality maybe SAM can directly work well. You don't have to train at all. But some of the image modalities, right? So there's a big difference. Then you do require some of the fine tuning. So for this case, I think maybe the good strategy is you directly apply SAM to your image domain and see how good that is. So if that's already performed like state of the art, then maybe or meet your requirement, right? Let's say your expectation is achieve like 80% accuracy, which SAM already achieved, then you don't have to do anything, right? So maybe the domain gap is not that big, or maybe this modality hasn't been seen in their training data. So you are perfectly fine with that. But if there's still some gap, and depending on how much training data you have, right? Let's say you don't have a lot of training data in your own domain, maybe you should leverage some of the efficient fine-tuning strategies we've talked about, right? Using adapter or LoRa, or maybe just specifically fine-tune some layers to reduce that gap. Okay.
Does ultrasound work well with SAM?
I don't think so. Yeah, I'm not sure if SAM V2 have that, because I know like in their later process, they incorporate some medical data in their training. So I think maybe V2 can perform, if you don't do any fine-tuning, it may perform well on certain medical images. But again, medical images are, like I mentioned, right, even like CT, X-ray, they can be very different depending on the imaging model you have, right? Different type of sensing devices, different parameters, they will generate very different images with different contrast and resolution, right? So it's in order for the model to perform better. So I think it depends on. Right now, we are trying to build upon or leverage a generalist or foundation model, trying to build a specialist, right? So you want to tailor a little bit using the customized data. That always works better if you want to have very good specialist, okay? So once, as you can see, right, so this, I took from this GitHub repo, so they basically list a lot of these different works that since the release of the SAM model, right, how people trying to adapt the SAM model in the medical domain, right? So some more notable like the SAM 3D, right? So this is maybe adapt SAM model for 3D volumetric data, right? So this is a 3D SAM adapter, right, by the name. So this is maybe specifically tailored for volumetric data like CT or X-ray, the MRI, and they are using adapter, right, to do the efficient fine-tuning, okay? And also you can find some maybe specific for some modalities, right, like a surgical SAM, right? So this may be designed for surgical procedure segmentation, right? So you have those surgical videos, maybe segment all these different surgical tools, all different organs, right? So they are specifically, maybe fine-tuned for some downstream data set. One notable model I want to mention is these MedSAM. Okay, so what they do is they take they do some initial testing for the SAM. So they found out for some of the imaging modality it doesn't perform so well. So they want to continuously maybe fine-tune it on the medical data. So for this MedSAM, what they do is they also collect a very diverse set of medical images, right? So this figure shows like a glance of how they collect different modality images and corresponding to different tasks, right? So here, we have different applications, right? We have the brain MRI images, maybe doing the brain tumor. We have this, this is maybe corresponding to the lung. And we have like a liver, this could be CT, X-ray, right? We also have the ultrasound, right? So this is the ultrasound image. And we also have other different body parts, right? So not just focus on the lung, brain, these major organs, but we also have different bone, like spines, right? And also we can throw in more modalities, right? So these, this pathology, right? Whole slide images, right? We also talk about that. That's also very important medical applications. And we also have these like common RGB videos, right? So this is like surgical, right? Maybe doing the endoscopy, right? So images, and also some surgical videos, right? Skin cancer, right? So these skin images. So basically a very diverse medical image data set cover various tasks, right? I also forget about mention these fundus image, right? So maybe also OCT image as well, right? So we'll also talk about that for the eye disease treatment. So basically you can think about they cover all different modalities, right? Different, disease, different organs, different tasks. So they fine-tune the model on these very diverse medical data. So they come up with so basically they are adapting the SAM for the medical domain, right? So this become like a medical foundation model, right? The MetaSAM. So once they train this, then basically you don't have to fine-tune anymore, I believe, because they already cover all these different image data and all different tasks, right? So without even fine-tuning on your own data, you may achieve very good performance, okay? So that's the MetaSAM is actually published in Nature Communications, so it's a really good journal. So, if you are interested in apply these medical segmentation or foundation model, maybe you can look into this MetaSAM, okay? This is just some figures, right? So they have all these different modalities, where MRCT into, going to the OCT, the morphology, right? Fundus, right? Pathology, right? Different modality. Although there's some kind of unbalanced distribution, right? So ideally you want to have a very balanced distribution, but probably it's because some of the, modalities don't have a lot of data, or they are also maybe crowdsourcing from public database. This is probably the only public available data set they can collect from. Okay. There's another paper which I also note here is maybe you should also take a look at it. For the detail is how to build the best medical image segmentation algorithm using foundation model. A comprehensive empirical study, right, with SAM. So they kind of analyze different aspects, right? So they come up very good, like a training or fine-tuning recipes, right? So if you want to build a very good, medical image segmentation, if you want to leverage these foundation model like SAM, so what is the training or fine-tuning recipe you can follow, right? So here, just to mention one of them. So I haven't looked into the details of this paper, but I read this a long time ago. I feel like there's maybe very good insight for you to learn, right? If you want to fine-tune this. So here they say, okay, if you have task-specific data set only, right? So you have image plus mask, right? You can do this kind of supervised fine-tuning, right? So basically you only have the task-specific data set. But if you have like more, right? So you can expand the data set, then maybe you can do some, later you can do some like multi-task agnostic, like self-supervised manner, right? So you can build these kind of different steps to adapt this model to perform better in your specific medical task. So yeah, they also released the code, right? So how you can fine-tune the SAM in this different training stage. So you can follow this recipe and maybe for your own application, okay? Okay, finally, I also want to mention this one model. This is Biomed GPT, which is I collaborating with other researchers from different institutes. So this is a general model, not specifically for one task, but is trained on multiple tasks. It's especially like a general model that can train on vision, language, and other modalities, and able to perform multimodal tasks. So that's why we call this biomed GPT, right? So it's especially able to perform various biomedical applications. So let me skip this, just go to this one. Okay, so basically when we train this model, right, so again, we are, consider all these different image modalities, like MRI, these fundus images, right, and pathology, right, whole slide images, and X-ray and the skin dermatology for dermatology. And we also consider various popular tasks, right? We can do the captioning. So basically giving these images, we want to generate a caption, right? Describe this image. And we can do object detection, right? So for this fundus image, maybe we want to detect some of the, the blood vessel leakage or something like that, right? Or maybe some of the function degeneration. And we also have the very, basic like classification, right? Different skin cancer type. We can also do some ink painting, right? So we can predict what has been masked out in this chest X-ray. We can also do visual question answering, right? So this is like just like the general VQA, right? So feeding into image, and we ask a question, and the model is able to provide the answer. Okay. And this is basically an overview, right? How this biomed GPT compared to the previous state of the art. So there's one also a very general model that is developed, from Google. This MedPalm. So it's also a foundation model that is designed for multiple, biomedical applications. And this is how we are able to outperform them, right? So we have this radiology VQA, pathology VQA, report summarization, breast mass classification, report generation, right? So all these different, and another one have this captioning, classification, VQA, all these, we're able to outperform the previous state of the art. And in terms of the method, right, so basically we trying to, is able to take all these different, image modalities, right, and also different tasks, they have different format, right? So if you're doing captioning, right, you have to dealing with images and text. And if you're doing object detection, right, you may have like a bounding box, right? So you have a couple of coordinates and specify the location and also the height and width of the bounding box. So to train this model, right, taking different format of the annotation and the images, we have to come up with some of the unified like encoding strategy. And once the model is trained, we has to be task agnostic, right? We are able to predict, generate a very unified task representation to support different types of tasks. So to have this kind of modality agnostic representation, so for images, right? So or for this kind of bounding box, we are using this kind of pixel sequence, right? So basically, we can using these pixel to sequence approach to generate this embedding or encode these location tokens. Okay, so because we are using these coordinates to indicating the location of the bounding box. And for this, text, this is, basically we can using some BPE encoding, right? Just doing any of the normal text. And for images, we are using the VQGAN, right? So basically we can using some dictionary and building that dictionary to generate these tokens, okay? And so in this case, we construct this kind of unified vocabulary, right? So we are able to deal with these locations, text, and different images. And for the model, okay, so we are basically using the vision transformer architecture, right? So we are able to, there's not much new here. Again, we are using this kind of self-attention and using the standard MLP, fully connected layer, right? The layer normalization, all these things, to encode these features and able to outperform, specific format depending on the task we trained on. And all these data set we are collected from the public available, so we are not doing some private data set collection and train the model. All these models we are collected are publicly available. We are basically, these are shows you, right? So what are the different, the contributions of these data set to the overall training data, right? So a lot of them are for the VQA, right? So because I think that's a very popular task or applications in the medical domain, because you can understand the image and also output some of the text description, right? And once we train this model, we apply these Biomed GPT to 25 data sets, okay? And for each of these different data set or applications, we are compare against like the best performing model within that individual task. Let's say I'm doing this chest X-ray, classification, right? So we are applying this Biomed GPT to chest X-ray, but we are also comparing whatever the best model for the chest X-ray database. So we are compare against these kind of the best specialist model. And out of these 25 data sets, we are able to achieve 15 of them is able to achieve the best accuracy or performance out of these 25 data sets. So which shows that this Biomed GPT is perform really strong, right? So out of these 25 data sets, we are able to achieve the best on 15 of them. And this is some other, and the second part of the table, showing you all these different data sets, how we perform compared to state of the art. Okay. So one thing I want to maybe mention for this Biomed GPT is, so we are open source the model, so it's actually available on the GitHub. So if you maybe want to apply this, you can directly download the model and do some prediction. I think one good benefit for this Biomed GPT is that it can help in some cases where maybe there's hospitals or maybe facilities that is under-resourced, right? So I know a lot of hospitals, maybe they don't have enough physicians, right? Or maybe a lot of the applications like do some kind of pre-screening, or maybe you can using the Biomed GPT as like a chat box, right? So they can interact with the patient and do some initial consulting, right? So the patient can quickly provide some of the symptoms, then the Biomed GPT can maybe provide some initial suggestions, or maybe suggest, right, what kind of specialist you can see, right? So I think this is really democratize these technology, especially in this kind of under-resourced places, right? Because a lot of like developing countries, right, they may have a lot of doctors, or they may a lot of patients or people don't have access to these doctors. I think even in the U.S., for some of the specialists, I think you have to wait or book an appointment maybe after 3 or 4 weeks later, right? So if we have this kind of technology, right, at least can help you, give you some initial insight, right? So, and also maybe if you don't know which, as I mentioned, right, if you don't know which specialist you want to see first, then maybe this will give you very good answer, okay? Finally, I want to have some of the discussions, right? So maybe a couple of points is with a lot of these hospitals, right? So this kind of EHR they have very large database on the EHR, right? So this basically contains all these medical record information about a specific patient, and even a history of the patient, right? If they visited the hospital multiple times, right? So these information is going to be there, right? So the EHR may also contain some like the vital signs, right? So other informations. So we can readily incorporating EHR with this very rich information, right? And combine with other images, right? To build this foundation model. And also, I think one benefit of really good merit we want to have for the AI model is to do some personalization, right? Because we're now talking about the precision medicine, right? Different patient, even for the same disease, right? So how they progress, how they react to a specific treatment, right, can be very different, right? So some of the patient maybe react to the treatment very good, but some of the patient may not, right? So after a couple of weeks, their condition maybe go back to the original condition. So how we are able to take this kind of personalized information and fine-tune this model into a personalized model, I think that's really useful, right? Because that's kind of customized to an individual, right? So that's going to provide a very accurate information to that specific individual, okay? And also, of course, finally, the impact on the healthcare accessibility is really important, right? So, building this foundation model is really, great, right? I think there's a lot of excitement. A lot of these doctors and physicians, they've heard about how good these AI models are, and they get excited about this, and they are gradually trying to embrace these AI in their practitioners, right? Or even help them to streamline their practice, right? So some of them, like appointment scheduling, those things can be done automatically, right? But how the accessibility still is a question, right? So how, if we want to deploy a model in the hospital, right? So how we can train all these staff, right? Like nurse, which is a large body of the staff in the hospital, needs to be interact with this AI model, right? So how we can make this model accessible to them and easy for them to use is also something we have to think about, right? So we don't want someone, like take forever or take a long time for them to learn or train them to get to used to this model. Then a lot of time they just feel like, bring overhead to them, right? They can easily burn out if they want to learn more new things. So then they try to stay away from them, right? Because you are creating more burden for them, rather save their time and improve their efficiency. So I think that's also something we want to make sure the model, the accessibility, and also how practical the model is really able to deploy in the real world scenario, okay? So yeah, so those are some of the points. But if you have any other questions or any other points you want to discuss? Yes?
I think in case of biomed GPT, when you were showing this radar plot, the performance of this report generations were pretty low. Do you
Which
know
one?
why is that the case?
Which one?
In the radar plot.
The previous one or this one?
No.
Oh, the later part, right?
Yes. Like report summarization, it seems like 20, 25, 30%. Do you know why is the reason of such low performance on?
No, it's not 20%, right? Oh, this one? This is like 60.
On the right.
On the right, this is 20. 20 is the inner. Some of them like 25%.
Yes.
So are you talking about this specific one?
Yes, report generation and report summarization.
The summarization, let me see. Oh, okay, this one. Yeah, this 20, less than 40%. Yeah, depend on the metric. And also the generation part, right? Because depending on like how long the report you want to generate. And the ground truths can be, it's hard to, to judge, right? So like even this is like less than 40%. Some of them, you can say is not very accurate, but depends on the ground truths, how the ground truths look like, right? So is the model generate something that is totally useless, or the model is maybe very verbose and they are generating something that may necessarily the same as the ground truth, but the information it provides can also be very accurate, right? So I think it depends on the metric. Of course, we are still not the level of like a physician or radiologist, right? So, but keep in mind, these biomed GPT is just a general model, right? So it's not trying to excel at all these models, trying to achieve like 90 or 100%. Otherwise, then the problem is already being solved, right? Then we can deploy this model to all these medical hospital settings and is able to perform maybe way better than the physician. Then the doctor will be panicked, right? So, these models will take in their job, right? But here the point is that we are just compare with some of the state-of-the-art model, right? So this is also a generalist model, and just to showcase, right? For some of the tasks, across the board, right, on average, we are able to outperform them. But I understand, right, so for some of the particular tasks, we are still a large gap, to the desired performance. Yeah.
I said you have a very high jump on the radiology AQ, right? So is it because that the data set that you are fine-tuning on has some specialized kind of a questions which gives it an edge over?
Yeah, so that's also a possibility, right? So an easy way we can fix this, maybe increase more data for this particular task, right? So here, maybe for this X-ray, chest X-ray data set, right? We can increase more training data so that, for this particular task, we can improve the performance. So yeah, I have to look into like if we have some data imbalance issue here.
Right.
Yeah.
And last question, do you have any human evaluation results on that, for example, as compared to some new MBBS students or residents, and how well they perform as compared to this model?
Yeah, it's a really good question. So I think this work was in collaboration with a lot of institutes and also including the Mass General, Harvard University. So they do have some medical interns or medical student and do some pilot study. I don't think we have this in this paper, but I think in the follow-up work they are actually deploying this and getting a lot of human feedback. So to your point, right, so getting a lot of human feedback is really important, right? So and see how the model is aligned with the human preference. So that's, I think, maybe the next step. We can further improve the model, yeah.
Do you think you can have like a mixture of expert kind of approach, for example, for every individual task where you need some specialized model? An expert can be like outperformed, or a group of experts can outperform an individual specific task?
So you want to tune this model for specific tasks? No?
So for example, in case of mixture of experts, you have certain experts.
Yeah.
And for each expert, it's specialized in particular task.
Uh-huh.
So let's say you can boost the performance of report summarization and generation.
Yeah.
Using some expert models.
Yeah, definitely. So yeah, I mean, that's depending on the purpose, right? So here we just want to demonstrate a general model that can perform a good performance on different tasks. But definitely you can using, mixture of expert, right? And train this or adapt these expert on a specific task and modalities, right? Maybe we have a mixture of expert only for report generation. We have another set of mixture expert that is for object detection, right? Another set is for different things, right? So that's how this natural large language model is doing, right? So out of all these mixture of expert, right, for a specific task, only a sparse of them will be activated, right? So to do the performance inference. So we can actually build this as well. But again, train such a large model with a lot of mixture experts, right? Thousands or even millions of them, the computation, those are things we have to consider. Yeah.
So how would you deploy something like this in the real world in a hospital? Would you use like cloud, or would you actually set up a cluster inside?
Yeah. So the easy way is we haven't gone to the efficiency point of view aspect yet, but obviously this is a large model we are building. The easy way will be and also taking granted into the privacy, data sensitivity issue. I think the straightforward way is we have to deploy this on the hospital, and then maybe the hospital can have their own server, so they can run locally rather sending the data as a cloud service, right?
So you'd have to pay for the hardware. You'd have to pay for machine learning.
I mean, the model, if you train, right, you just do the inference. I mean, if they want to buy, if this is a commercialized model, and then they would have to purchase the software, like the license, and then if they have the hardware to accommodate, right, they can install that on their hardware and do the inference.
You also still have to have a doctor to confirm this.
Yeah, definitely. So because I think a lot of healthcare settings, always AI and a human should be in the loop, right? Always have to be like AI and a human teaming, rather AI replace the human. So a lot of tasks. There's actually some very interesting findings. I listened to a podcast from Stanford. They're doing medical AI. They mentioned some of the model. You would think AI and the teaming is always going to be the case, right? But actually they found some of the applications or cases without human intervention, AI model actually is able to perform better. So definitely we need to examine this case by case, right? So if for some of the tasks, like a very simple, repetitive, easy task, definitely, I don't think maybe we need any human involvement because the accuracy is already high. But for very complex, we definitely need human oversight, right? Because like all these very complex cases, right? If you have to, in the hospital, you have to involve like pathologist, radiologist, right? And also maybe other doctor specialists together to determine a case or come up with a treatment plan. I don't think this can be done by a single AI model, right? So in this very complex cases, definitely we need human supervision. And I think we are only kind of scratched the surface of that. There is still a long way to go. Yeah.
I guess not to challenge the statement of needing the human supervision, but I guess actually one of the things you had brought up like earlier in the semester was the potential like bias that a
Right.
doctor or practitioner would bring.
Right.
I mean, do you see the generalistic kind of AI models as potentially augmenting that, or like augmenting the bias, or I guess mitigating it?
So it all depends on how the model is trained, right? So if your model, the data inherently has some bias, right? So